1, March 22nd. All right, let's do it. Number of ways to arrive at destination. You're in a city that consists of n intersections numbered from 0 to n-1 with bidirectional roads between some intersections. The inputs are generated such that you can reach any intersection from any other intersection, and that there is at most one road between any two intersections. You're given integer n and a 2D integer array roads, where roads, okay, so that's an edge, and this is a kind of a cost. Means that there is a road between intersection u and v that takes time, minutes, to travel. You want to know in how many ways you can travel from intersection 0 to intersection n-1 in the shortest amount of time. Return the number of ways you can arrive at your destination in the shortest amount of time. Ooh. The shortest amount of time. I mean, we can Dijkstra it first to find the shortest amount of time. So in this case, if we Dijkstra, then we'll go here. So it's 2. And then, right, and then we how does Dijkstra work? Yeah, so we have 4, 6, this one in, and then we can get out. And we have these are all 5, so I can pick any of the 5 out. Then put it in. That's actually 8, right? I have 5 out. Yeah, 5 out. Yeah, 7. Right, 7. Shortest takes 7 minutes, and then you just need to find how many different ways to go from here to here. It takes 7 minutes. 7 minutes. So you can do it. DFS, right? Basically, start from here. You know 7, so you just go, right? Go, and you have 7 minutes. Go, and then you don't want to go back because going to the visit 1 doesn't really work. So yeah, so we'll Dijkstra first to find the smallest distance, and we'll DFS to find how many different ways. But this is really scary. Which kind of means we don't want to okay, so I have 200. At most one row connecting any two intersections. It can reach any intersection from any other intersections. And then we have to modulo it. Huh. So I know the shortest amount of time. I was going to say just, try every path, but this is scary. It looks like it can be a lot more different ways. which is true. Like we can have something like this, right? We can have a start, and then we can have like that, and then each one we can have this, right? And then each one can have again similar. So, and then eventually everybody all go down to the destination. So you have to really compute. I think this actually screams maybe BFS will work. How would BFS work in this case? So if it's BFS, we start at 0, right? Next it's 4, 6, 1. So this is already done. 4 and 1. We have a 6. For 1 we have 3 and 2. And for 3 I have 6 and 5. For 2 we have 5. And for 5 we have 6. And now we can keep track, right? We can keep track. So there's a 2, there's a 3, 3, there's a 1, 1, 1, and 3. Oh, this path is not good, but this path is good. I don't know. How many different ways? I don't understand. Oh. Okay, comment. Bring your tea. Alright, I'm back. I'm trying to see, like, is this a trick? Well, for one thing, you can only go down, right? And there are only 200. Oh, there might be multiple, right? There might be multiple. Ah, I see the trick. I think there might be multiple connecting. Ah, I see. I see. So, yep. So for example here, right? So we have 0 to 1 with 10. But, you know what? Let me just try this. I think that's why they say there might be a big number. So I actually gonna have to do 4. Oh. Wait, what's that? Oh, the roads has... Huh? I don't understand. I don't understand. You see, to me, every pair can have at the most 1. Because that's how it calculates this, right? Because you have n nodes. So one node, if it has everything to everybody else, then that's n minus 1. This is 1 plus 2 plus all the way to n minus 1. That's what this is. Which means we don't have 1 connecting to each. And we only have 200 nodes. How do you get to, ever possible to get to a big value? Right? How do you even get to a big value? I can literally go through all possible, right? All possible ways. I can go through all possible paths. I can even DFS at this. Because the visited one, I just don't visit again. And what's the point if you visited something and you visit it again? And it has to be connected. Well, you do visit again. Like in this path, you visit it, but in the other path, you visit as well. So yeah, in the path, right, in the same path, we don't visit the same nodes 2 times. But if it's a different path, we visit again. So in total, it's O(n) squared. Because just essentially it's each edge gets visited only once, right? Each edge gets visited only once. And you just do that. I don't know. Why would it be a big value? I'm gonna try just to see if it's bluffing. I cannot figure it out. Seems like it's just bluffing. How could it produce like more? Because different ways is just different paths, right? It's just different paths. And if in a path, you really can't go back and forth. Like you only visit each node only once, because it doesn't make sense to reach a node twice. So it's just the number of paths, and the number of paths is, I mean, pretty, I don't know, right? I really do not know how this can be, right? I mean, I think BFS might be an easier way to go with this. But anyway, so we'll start with the graph. Yeah, let's just try it. I mean, it shouldn't take too long to code this up. I think I don't need this one. I just do this. Right, and then we say right, so this is the graph. Then we say a Q. Right, all we need is a Q. So we can say, we can do a deck of, or I do think we need a, let's say a pair. Right. And then we'll put, so it will be what will be put inside. But that doesn't make sense, right? Because if you do a deck and coming here, and then this go to 5, this is also go to 5, right? That counts as two different paths. That does count as two different paths. Yeah, we keep the minimum, right? We keep a minimum of the so we say std vector of int, because if you hit something that's larger than the first time you hit it, then there's just no way it can produce. No, I can see, no, like I can, if this can be a bigger value, right? So I can hit here with a bigger value, but then from here, wait, hold a second. So if a node can be reached at a different time, then definitely a smaller time will produce. No, not really. The smaller time. Hold on. So one is a bigger time, the other is a smaller time when you reach a node. So we always want to reach a node with earlier time, because if you reach a later time, no matter what you do, it's not going to be good. So that should be the minimum, right? So the minimum time when you reach a certain vector, right? So we should say that's going to be n minimum time, and we can set the minimum time to be, oh, I don't even know what. I can just do max, right? I can do int max. Okay, so now I have a queue. Now I have the minimum time, and we'll say min time 0 equals 0. Well, that's because you start, right? And q dot push back 0 is 0 time, right? And we say while q is not empty, right? Q is not empty. Then we say auto element q dot top front q dot pop front. Okay, so we get the element out, right? We get the element out, and we have its current cost, right? And then we say for child of graph element 0, right? And then say if ooh, that's not right. We also need, oh my goodness, we need a few things. That should be a pair. Should be R1, R2, right? Okay, so this is not right. I only have element. So yeah, I can't still call child. So here shall be dot first. Right, first is the node, second is the time. Now we shall check, right? Because then it's just like Dijkstra. Aren't we just doing Dijkstra in this case? Right, then we're just doing Dijkstra. I still don't know what the trick is. Why would it become a lot? Hold on. I think I know. For example, if 0 to 1, I can add another one. I think this is where it gets a little bit tricky. Right? If I add another one, and I don't do this one. So basically I add another one, which I think is allowed. Repeated edge. So you can have repeated edge. I don't understand. I think it's just Dijkstra. I really think it's just Dijkstra. Which means if we want to do Dijkstra, then this is just going to be shall do priority queue. Push. Oh, is that max or I forgot. It's a max priority queue. So we'll push cost and node. it should be a negative. So cost element dot first, and node should equal to element dot second. So basically we say if the cost is larger than mean time node, then we'll continue. Right, so it's too big a cost. Otherwise, we'll get a child of the node. So if child dot second. Right, so this is going to be node and cost. Right, so if the child dot second is this thing plus cost is smaller than if it's smaller than mean time child, then mean time child equal to child second plus cost, and q dot push mean time child and child. Right, mean time child first. Okay, so all we need to do is if it's bigger, then we go. Otherwise, then we can check, right? We can check if we reach the end, then we just terminate. We say if node is equal to n minus 1, node is equal to n minus 1. So I only have a count. So the rest equal to 0, right? Row if equal to n minus 1. And because along the way it will change. So int I'll have mean time t. Can say if mean time node smaller than t equal to mean time node plus equal to 1, else if node is equal to t and rest plus plus, and then I'll continue. I don't know, I'm just putting something together and then trying to see if it works. Okay, because this is why would they stop? I don't know. Because I should say smaller equal to. Oh. Interesting. Really? You have a timeout if I do smaller equal to? Okay, then this will give me the shortest then. Then we don't do this. We simply we will record, right? When this is equal to this, then we'll break. Right, then we'll break. So we hit it, then we'll break. Alright, then we'll do, just go through everything and trying to see if we can find one that's and I also have the minimum time, right? Which means if we do another round of BFS, every time we push a new thing in, we'll check, right? If it's equal to, we push it in. If it's larger than, then we don't push it in. So we basically have, now we're gonna do, so let's do this. Dijkstra to find the min time to reach n minus 1 from 0. Okay. And then BFS to find the number of paths. Oh. Right. File q.empty. Right, so we have the q, and then we have costs equal to node and cost. Oh. Right, so we got this and this, and but isn't this the same thing? I feel like it's the same thing. If child dot second plus cost smaller equal to min time child first, right? I feel like it's the same thing. This is fine. Now we go node first. If node is equal to n minus 1, rest plus plus, continue. I don't know. This just feels... That's interesting. Child of first is there's another one. What the hell? What? Well, I mean, this I think probably is wrong. Maybe. Okay, 0, 0. Right, so I have this, this, and this. Child, that's in the graph. The second is cost. Smaller or equal to meantime child of first. What's wrong with that? Yes? What's wrong with that? So let's see the child first in meantime. Yes. 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 Oh. Alright. That I guess it's okay. Probably have to be pushed back. I got like 2 Q's. Yep, that's kind of getting things confused. I don't know. I'll run it. Okay, so we got a wrong answer. Huh. What in the world? Okay, I guess I have to first figure out. Let's see, meantime n minus 1. Do we have an end time? Huh. How? What? Huh? Oh, we have these negative. What the hell? Oh, we forgot to put negative in it. Jeez. Oh, Lord. Then how the other one pass? Very interesting. The other ones pass. Now, this is interesting. Expected one is 66 different ways. Now, this will time out. hold on, let's solve this one first. So we get a negative. So when you push, this shall give a negative. Right? But you really have to go through all those things, all those paths. But still, like I don't understand how it is possible that we can get so many different ways. I don't understand. I don't know, I'm gonna try it again. Huh. Oh, it's TLE. But why? How? I don't understand. And for one, we might get. Hold on. This size. Okay, the time itself is also an issue. Which means this cannot be int. I think this has to be long, you know, just in case. It's a cost. Let's get long. I don't know. Maybe long works. No, I don't think so. No, long works. I'll just take a long time. So this is also long. Yeah, it's on timeout. Wait, how? But I still don't understand. That's the thing. I don't understand. This is on timeout still, but yeah. But how? How is it possible that you can produce so many different ways? Well, essentially, you just have everybody connecting to everybody else, right? That's what we have. 0, 1, 0, 2. We probably have 0, 3. So every node's okay. So let's think about this, right? So you have these nodes. It's a complete. So every node has a path to every. That's just probably too complicated. Let's simplify it. Let's do 4. Okay, 0, 1, 2, 3. Right. So every node will connect to every other node. Right. That's essentially what it is. And we want to know how many different ways from this to this. Right. Now, if we structure it in such a way that it costs the same to go from here to here, for example, because you have different ways to get there, right? You have different ways to get there. So let's say we took, it requires 6, right? And then we have 3, 3, 3, 3. And then this one is going to be 3, 3. That's not good. So let's give them 2. Okay, let's get these 2. All right, so I have 2, 2, and then this one's also 2. So now all the paths Now this path is 5. Alright, I still think Dijkstra is necessary. Okay, I think Dijkstra is necessary. It's the second half. It's probably troublesome. Let's see if Dijkstra shall work, because Dijkstra does not go repeated. So if I also get this one, use this test case, right? So if I go this, I shall be able to get the runtime for everyone. Yep. So this is for this. You can see this is this. This is this, right? We can get all this, but we do not get is the. Look at this. This is a gigantic number, right? This is a gigantic number. How? So basically, the question turns into: given the path, and we want to know how many different paths can we get to the destination with a given total weight, right? That's essentially what we're asking. What I do not understand is how come there could be so many different ways. Well, okay, so it's not each path visited once. A path can be visited many, many times. Okay, well, fair enough. A path can be visited many, many times. So maybe what we can do is, the smallest, I don't know, hold on. So how many different ways to, let's do it this way. So this is the destination, right? And now we can have, let's say, 2 nodes come into here, right? 2 nodes come into here. So for here, the answer is going to be the total number of here plus the total number of here, right? Right? The total number comes, like, we can have multiple nodes, so just because that's independent. Now we were not going to be going up. So now the question is how many different ways to get to here, to get to here, to get to here, right? It has to be minimum, right? How many different minimum to get to all these, this spot, and this spot. And then you keep going all the way to the top. But how does that make this simpler? Well, Dijkstra will give you the minimum for every single node, right? Okay, so you have the minimum for every single node. Yeah, it will be like, if we have, let's say, 10 different ways to get to this node, when this go down to its children, right? So you say how many different ways to get here? So there's already 10, right? And then this one will have another one coming in. I say this is another 10. So for this one, I say I have 20 different ways to get here. Okay. So what? So if it's a queue, right? I need examples. I need good examples to help me understand this. So we start from some node, right? So we go here, and we know it has to be the minimum, right? It has to be minimum. So if it's not minimum, we just let it go. That's exactly what we're trying to do, right? And can we just I don't know. Maybe we can use this as an example to probe this problem a little bit more. Let's do some print debugging here and see if we, hit something multiple times. Things like that. Just, kind of just get a feeling of it. Okay. So in this case, this is the start, right? And we hit 1, 2, 4, 5, 6, and we hit 2 again. 3, 5. Yeah, we are repeating ourselves. You see that? Yeah, we're repeating ourselves and hit them multiple times. That's why it's not a good solution. Because you start from something, and everybody's connected. You start from something, and you go, right? And then you go. So in this case, we have 0, 1. Yeah, let's just map out a little bit. Just map out. I really have to kind of give myself an idea. So 0 to 1, we have 2, 3, 4, 8. Right, now 1 to 2, we have 2, 8, 5, 2. And 2 to 0, yes. We have 5, 2, 0, 0. Wait, that's not a circle. Right? And then 3 to 1, we have 1, 2, 4, 8, 0. And 2 to 3, we have 9, 6, 2, 8. It doesn't matter, right? So when we start, we have 0, 0 point to the 4 as well. Right, 0 to 4 is 2, 2, 1, 9. 2, 2, 1, 9, 5. Let's remove this one. I think that, 0 also to 5. Right, 0 also to 5. 0 to 5 is 2, 7, 8, 6, 3. And 0 to 6, right? So all that. So from 0, we go to every, we only go to 6. Right, we only go to 6. So we also 0 to 6. 0 to 6, 2, 8, 6, 9, 9. Okay, 0 to 6. 2, 8, 6, 9, 9, right? So that's when we start. We start with 0, and then we go to 1, 2, 3, 4, 5. Does 0 go to 3 too? I'm not sure. I didn't see 0 to 3. Ah, 0 doesn't go to 3. Okay. So yeah, so I go to 1, 2, 4, 5, 6. 1, 2, 4, 5, 6. Right? And then these are all minimum, I suppose. And next, from 1, I go to 2. Right? So essentially 2 has 2 ways. Right? 2 has 2 ways of getting here. And then we go to 3 again. No, No, we got 3 for the first time. And then somewhere we can go to 5. Maybe during Dijkstra we need to figure out how many different ways. But I don't really think it's a Dijkstra issue. Right? How could it be a Dijkstra issue? It's just like, there's so many ways. Oh, I couldn't wrap my head around. Like to reach each node, what's the total number of ways to reach each node with a minimum cost? Well, each node has a certain number of ways leading out, right? Or when we do DFS, right? When we do DFS, because right now we will revisit a node. We put a node in it again, right? But instead of doing that, maybe we can keep track of how many times a node has been hit. What do you think about that? How many times a node has been hit? We don't push it inside, right? We don't push it inside. Right, we have a visited set. So when a node is being visited, we don't push it in again, but it can be, we can arrive at, right, if it's smaller or equal to the mean time. That should just be equal to the mean time, right? If that is the case, then we'll increment. That's the number of ways we can hit, right? There's a number of ways we can hit, but without us having to put it in the queue again. So in the queue, we are guaranteed only one. Each node appears only once, right? Appears only once. Now from here, then you will move on, right, to the next. So when you move on to the next, you have to pass down your count, but the count is still increasing, right? The count is still increasing. So you pass down your index, your parent, right? Your parent. So you say, for me, my parent is this. You have a bunch of parents, and okay, so at the end of the day, when everybody gets to the end, the last node can have a collection of parents. Like who can go to the end node to like make it viable. So I have the end, we have this, then all I need to do is to check there, right? To check how many things they have, right? So to check how many nodes they have, I have to go a step further, go to find their parents, right? I go to find their parents, and all the way down to the top, all the way down to the top. Wait, hold on. So you're saying that we'll keep track of how many times each node gets hit, right? How many times each node gets hit, but we don't put it inside. Okay, we keep track. This node gets hit this number of times. This node gets hit this number of times, and it's all the smallest, right? All the smallest. The smallest. This node gets hit this number of times. This node gets hit this number of times, and I'll keep track. Yeah, but I just add this. Okay. So this node will pop up, and then I'll go to the next one. So the next one says, okay, I can get a parent, right? I can get a parent from this, okay, and I can get a parent. I can get a parent. So eventually, each node has a bunch of parent. Each node has a bunch of parent. Then we work backwards. We work backwards. Is that what it is? I don't think so. Let me think again. We hit a node, right? And then it's the first time. We say this node is hit once. And then we hit the next node. I hit the next node. But this one has already been hit. So I don't keep it in. Right, because it's already in it. But I count this one has been hit, like say twice. Right, and now when this go to the next, so yeah, we just say, okay, yeah, this node can be hit by these, right? And it depends on I mean, from the start, I'll have a certain nodes that are minimum, right? We know which ones. So we get those nodes out. These are the minimum nodes. And from each of this node, I can go to the next round of the nodes. And if the next round is a new one, it's a new one. If it's the one that has already in there, I would just increment the count. Right? I just increment the count. And so yeah, as the first level, from the start, I'll go to the first level. Okay, so they all get visit once. And then from the first level, I try to produce the second level. And when I produce the second level, I'll have new nodes. Or I'll go to the node that has visited before. And if it's the same, then we just say that node get visited more than once, right? The ones that visited before more than once. So we have the new nodes, and when those nodes get down, right? When those nodes get down, then it passes down number, right? How many times it can do. Alright, I think I have to see the solution. I don't know. DP. Maybe we need a DP. Using those edges only, the graph. Yeah, we can get the minimum cost of every single node. And then we use dp to do this. How do we use dp to do this? Okay, we can say, let's say dpij is the number of ways to go from I to j, right, with cost at j being minimum. Right, from I to j. Okay, so we say dp like 0, 1. Do we know if it doesn't go to 1? What's the path to go to 1? Yeah, I don't know this. Screw it. I'm gonna read a solution. I don't know. Path count. Ah, that's it. It's just a change in Dijkstra. Ah, I feel like I should have solved this, right? A change in Dijkstra. Hmm. Hmm. Don't do that. Hmm. don't understand. Hmm. It doesn't make any sense. I think now I know. There we go. Alright, that's it. I feel like this one should do this one again as well. Alright.